Hey guys, welcome to our second lecture on solutions, and this will be a continuation from where we ended up last time. Now, before we start, just letting you know that this lecture is going to be the same exact way. We will have an assignment after this, and also you should print out your outline before you start. Okay, now please, again, I had some issues with work that's being turned in, and please make sure you log on to Jupyter and turn your work in directly to Jupyter. Don't hit reply and send me a message with a attached with attachment in it. One of the main reasons is that I get a lot of messages this way from students, and I can't keep track. If you were to log it on directly to Jupyter, it will show up next to your name that you've completed it, and all I have to do is click on it and review your work and then give you a grade. So doing it the other way, sometimes I can't keep track, and I want to give you guys credit for your hard work. All right, so let's get started. So chemistry lecture 2, solutions and continued. Let's move on to point 7, electrolytes. What are electrolytes? Electrolytes are substances that produce an electrical conducting solution when dissolved in a polar solvent, such as water. The dissolved electrolytes separate into cations and anions, which disperses uniformly throughout the solvent. Now, let me just explain that really quickly. Is that normally water does not conduct electricity. Only in the presence of electrolytes dissolved in it will it start to conduct electricity. So, for example, if you have a shallow pan of water, distilled water, if you were to connect a battery to it, and then connect this to a, say, light bulb, and then you take this and you put it down there. Normally, when you flick the switch, current will not travel through water. Well, the minute you put down something like say, for example, NaCl, which is an electrolyte, into the water to create a salt water solution, what then miraculously will happen is that electricity could then travel from one side to the other, causing this light bulb to light up, and then as a result, that's an electrolyte. Because in solution, it creates the ability for solution to carry an electrical charge or current. Sorry, not charge. So that's what an electrolyte is. So therefore, if you need cations and anions to disperse within the uniformly in the solvent, then therefore, by all definition, all soluble ionic compounds are electrolytes. As you know from previous lesson, that because ionic compounds, the soluble ionic compounds anyway, will break up into mobile ions. It's metal cations and non-metal cations will actually disperse within the solution, so you need mobile ions. Example: distilled water does not conduct electricity, but when NaCl is dissolved to become NaCl aqueous, Na plus ions and Cl minus ions, or cations and anions, dissociate to create mobile ions within the solution, allowing for the conduction of electrical current. So therefore, because of that, what are non-electrolytes? Well, non-electrolytes are polar compounds that do not form ions. Well, as you know, polar compounds are polar molecular compounds are molecular compounds, which means they're both non-metals. So they don't have ions in there. So therefore, when you dunk them in water, they don't dissociate. They just realign themselves to actually interact with the the polarity of the water molecule. So they do not conduct electricity, and therefore they're not electrolytes. So some examples of non-electrolytes are sugars and alcohols. All right. Point 8, concentration of solutions. So solutions could be dilute or they could be concentrated, meaning that they have a relative amount of solute dissolved for a given solvent. So therefore, when you say dilute, relatively it contains small amounts of solute, or concentrated, they contain a relatively large amounts of solute. All right, so therefore, dilute and concentrated refers to the concentration of solution. But there is actually a better way to measure concentration of solutions. There are There are three things that measures concentration of solutions in the regions that you need to know. A, molarity. Molarity is a number of moles of solute dissolved in 1 liter of solution. So you can see it here. This is right off your reference table, the very back page, page 16, table T. Molarity is the moles of solute over liter of solution. So moles of solute means the number of particles of solute over the liter of solution. B, part per million. What is part per million? Part per million is the number of units of mass of solute per million units of total of mass. Parts per million is usually used for substances that are more dangerous, like say for example lead in water, right? You don't need a bunch of it in water to actually harm anybody. You just need a very, very small amount. So therefore we use parts per million for stuff like that. So therefore, or things in something that is very, very small amounts. So what is parts per million? Is the mass of solute over the mass of solution multiplied by a million, and you'll get your parts per million. It's in the name. You can see it there. You'll never forget that. And finally, C, percent by mass. You know percent by mass. We've done it before. Percent by mass is the mass of part over the mass of whole multiplied by 100. But since you know that solutions are also made up of parts, so in this case, what is the part in a solution? It's the solute. So you say mass of solute over the total mass of the whole thing, which is the solution multiplied by 100 to get that percent. Okay, so these are the three types of measurements used in solutions for the reagents. Number 10, colligative properties. What are colligative properties? Well, colligative properties are the properties of a solution that depend solely on the change in amount of the solute particles, not the identity of the solute particles itself. For example, meaning this: if I were to put more or put less solute in a solution to form a solution, something will change. Okay, what will change will actually be the colligative properties, right? So if I increase the amount of salt in a saltwater solution, something will happen, or decrease the amount of salt in a saltwater solution, something will happen. Okay, so what are those things that would happen, or what are colligative properties? Well, there's two colligative properties that you would need to know for the reagents. Number one, boiling point elevation. Solutions boiling point increase as number of solid particles increase because solid particles reduce the amount of solvent particles that are able to escape liquid phase. What do I mean by that? It means this. Say for example you have a water, and normally water will boil at 100 degrees Celsius. But what happens if you put you dump a lot of solute particles in there, like salt, for example? What ends up happening is that the particles of water that would normally break off and fly off into the air at 100 degrees Celsius doesn't do that anymore. It does it at a higher temperature. So, let's take a look and see if we can show you a rudimentary drawing of why that is so. So let's take a look at two types of solution. The first solution right here has, we're just gonna do the air liquid, air, and we're gonna kind of draw a dot. This is the surface. Okay, so normally if you look really, really closely, during an area where it's just water only, what will happen is that the water molecules, I'm just going to draw the water molecules as circles. They're not circles, as you know, right? They have oxygen and two hydrogens in them. So technically they would be like Mickey Mouse ears. But I'm just going to draw them circles for the sake of brevity. Normally, if you have pure water, all the water molecules will pretty much be right there at the surface like so, which means that at any given moment, these water molecules could then interact with the air, and then pretty much when you heat up the temperature, they move up, and then they start to form, they start to actually go into gas phase. Now imagine in a solution where you have solutes and solvent, where solvent is water. Say for example salt. Say for example you put salt particles of salt. It's not particles, it's actually sodium and chloride interspersed. So, but just bear with me. Just say for example you have intermediately anywhere along the solution, you have solute particles along with water molecules, like so. So they're interspersed along with the water molecules. So these are your solutes. Notice that they kind of block the way. Any solutes that is near the surface will prevent the solvent from going to gas phase. They're in the way. See, they're there. There's one there. There's one there. There's one there, and it creates a kind of gridlock for them to actually get through to become gas phase. So that's why I'm putting now. What do you think will happen if I even add even more solutes in here? Well, then there'll even be less space for the solvent to get through them to get to the gas phase. So what are some examples of colligative properties? Well, colligative properties you could, as an example, is when you're cooking, say for example, pasta, right? If you were to actually put salt into the water, not only would you get better taste, you'll actually have higher temperature, which means that it will boil faster. Oh, sorry, it will cook faster because it will increase the temperature at which you're cooking. All right, B, freezing point depression. Increasing solid particles in a solution causes its freezing point to drop. Why? Well, remember, from liquid to solid, liquid is forming crystalline structures or orderly patterns that it makes a solid. Now, what happens if you have stuff in between the liquid? Is it easier or harder for these liquids to actually form a orderly crystalline pattern? It's harder because now there are stuff in the way, which means that you actually have to decrease the temperature even further to force those liquid particles to solidify into an orderly crystalline structure to create a liquid. All right, so that's why, so you can imagine if you were to increase the amount of solute particles in the solvent, it's even harder for water to even do that. So it even lowers the temperature even more. So that's freezing point depression. Particles of, so examples. So what is an example of freezing point depression? Well, remember if you have ice during wintertime, how do you melt them? Remember, New York City would salt the roads, or your parents would throw ice on the walkways or the driveways so that the ice would melt. Well, reason why is because when you put salt in ice, it lowers its freezing point. So, for example, if the normal freezing point is 0 degrees Celsius or 32 degrees Fahrenheit, by putting salt in there, the freezing point will drop down to, say, for example, 15 degrees, to 25 degrees or even 20 degrees Fahrenheit, which means that if it's, say, for example, 30 degrees out, normally water will freeze. By putting salt on ice, you lower its freezing point to, say, 25, so it will become a liquid because then it's 30 degrees is not enough to freeze the water, so it'll just melt. All right, which brings us to number 11. Change in colligative properties is directly proportional to the number of moles of solute particles in the solution. We just explained that. Increasing the amount of solute particles in the solution will directly increase the colligative property, whatever you're talking about, whether it be boiling point or freezing point depression, making it higher or making it lower. Okay, so therefore, depending on particles, depending on which particles you're looking at, it will create more or less moles. How do you know that? Well, let's take a look at the first one. Magnesium nitrate. Actually, when you break it up into ions, that will be Mg2 plus, and then you'll have 2, because you see there's 2, that 2 NO3 minuses. So which means that for every one of these guys, right here, for every one of these guys, you're going to create one of these and 2 of these, or 3 particles of moles of stuff in the solution. So for every one, you get 3. Now, let's take a look at sugar. In this case, glucose. Glucose is a polar molecule. It's a molecular compound. How do you know? All nonmetals. So they don't break up. So which means that for every 1 mole of glucose, you get 1 mole of glucose in solution. So it creates a 1-to-1 ratio. So 1 particles in solution. Not so good. So this one gives you 3. This gives you 1. Let's take a look at aluminum bromide. That again is a ionic compound, metal, non-metal. So when they break up into ions, you'll have aluminum, which is a 3 plus, and bromine, there will be 3 of them, so 3Br, so 3Br minus. Remember, 3 pluses for every 3 minuses. This gives you again 3. 3. Oh, it gives you 4 actually. 4. All right, 1 and 3. And so, plus it says it there, dar. And let's take a look at HCl, or hydrochloric acid. This gives for every 1 hydrochloric acid just 1 H and 1 Cl, 1 H, 1 Cl. So this gives you 2. So the winner chicken dinner here is this guy right here. It gives you more for every one of them. It gives you 4. So actually the answer is over there as well. So therefore it gives you that. All right. Let's do some practice problems. And practice problems, you can do this on your own. And obviously the one that the more, when you break them up, well, this doesn't break up. When it breaks up in solution, the one that breaks up the most is the one that's going to give you the most amounts of solutes per solution. All right, enthalpy of solution. Now, sometimes when you're forming solutions, solutions could gain energy, or solutions could lose energy depending on what you're forming. For example, if you're forming one thing, it could release energy, so you'll feel the outside part of it will be like warm. Or when you form a solution, you'll feel it's cold because it's actually absorbing energy. So it could be endothermic or exothermic depending on what it is. Okay, now energy absorbed in kilojoules marked by a positive number. So therefore, every time you see a positive number, this is table I, page 5, the bottom 1, 2, 3, 4, 5, 6. You'll notice there's a positive and negative number. If it's a positive number, that means there's a gain of energy. It means it's positive. You're gaining positive. Okay, so therefore it's endothermic. Exothermic is a release of energy in kilojoules. It's marked by a negative number. When you're losing something, remember, it's a negative, right? Is it positive if you're losing money? Nope, it's a negative. Just it's a way to remember maybe. So again, so therefore this right here, when KNO3 is dunked in water to form K plus and NO3 minus, remember that's a dissociation, right? They dissociate. It's actually an endothermic. How much? Well, 34.89 joules. Kilojoules are released. Are absorbed. My bad. Positive number. Now, when sodium hydroxide is dunked in water, they dissociate. This is actually a exothermic. How do you know? It's a negative number. 44.51 kilojoules are released. Okay, so when you're reading table I on page 5, pay attention to the plus and negative, and that tells you if it's absorbing or releasing energy, endothermic or exothermic. All right, everybody, at the end of this lecture, you're to do properties of solution. That's the same, the packet. It's topic 7. This time you're going to read 124, 131, page 24. Do questions 24 to 50. All right, guys.